So today, the title of my presentation is the hybrid classical quantum approach to solve the heat equation using the quantum annealers. And still, I'm working on the fluid heat, solving the heat equations and fluid equations. And last presentations were about reducing the time by using the quantum memory layouts. And another presentation was reducing the time using the quantum amplitude estimation algorithm. And today, we're going to look at using the D-wave quantum annealers on solving heat equations. Now, so these are the my contents, and let's first look at what equation that we want to solve, which is heat equations. And briefly introducing the heat equation is that it just looks like seen in the screen, and the first three terms on the first rectangle is the thermal diffusion term, which is if the thermal conductivity K is a constant, it's Laplacian. And the second rectangle, that's a heat source term, which can be variant by the time, but usually it's just a constant, and it's the distribution or over the regions that we are interested. And the last at the right hand side is a heat conduction term, which is from the Fourier's heat conduction law. And today we are going to solve the steady heat problem, which is the time derivative of the temperature distribution is 0. So we only thing you have to consider is the heat source term and the Laplacian. And basically we're just solving the Poisson's equations. And introducing the boundary conditions just like that. And first one is the equation that we are going to solve. And and it seems like at the right figure, the temperature is rising linearly at the x equal L and y equal L. And to make this thing simple, I just set the L as a 1. And another boundary condition is about the heat source term, which is in this paper, he set the heat source term as a just random distribution of around the whole region. So it can be just simply made by using random function. And these are the boundary conditions, and these are heat equations that we want to solve. So that was a simple introduction about heat equation, which was very simple. We all have solved any Poisson's equations or Laplacians. And next I will introduce how it is solved classically, even in the research area, or in this case it's really simple, but yeah, how it is solved in classical schemes. And so computers cannot address any continuous real numbers. So what we have to do is pretty much we have to just discretize the whole region we are interested in. To do so, we have to use the Taylor expansion. And in the equation we want to solve, there is a second derivative about a x and a y. So we have to make a proper approximation for the second order derivative of the temperature. So we just now, let's say we discretized the x-axis as dx, and by using Taylor expansion we can approximate as a follows. So our Laplacian would be seen like this. It seems there are many terms, but it's just it seems like a average of if let's say if this is equals 0, it becomes the Laplacian of the 4 neighboring grids. So yeah, we will gonna substitute that discretized term into our equation. And this is the result. Now, as you can see, this is just an we started from the Laplace equation, Poisson's equation, but now we have to solve a linear systems. And oh, sorry, there's an error. So basically, this is how it is solved classically. We discretize the domain, and now we change the Laplace equation, Poisson's equation to the systems of linear equations. Now, this is the main part, which is will introduce how it is solved in this paper. So this paper uses the quantum annealers. Now, quantum annealers uses series of qubits to find the least value of such a function. And finding the least value is equal to finding the combination of spin that makes the ground state, which is just an Ising model that we have learned in the mathematics for physics class. So, but there can be a question now. So we want to solve the linear systems, but this quantum annealer seems like an optimization machine. How it is related? And there is a prior research that solving the system's linear system, which is ax equals b, is equal to the optimizing the following optimizing that equation on the screen, which is, and this is called QUBO algorithm. So now we have to address the real values. So each component on this x here would be the real values. Each component will be the real values. So to show the real values at each component, we need R qubits to represent a real number at this range. So just using the just to show the r dimension n-dimensional vector, we need R qubits. Now we're going to substitute this into the equation that we want to optimize, and it is shown like here, which is very similar to the Ising model you have seen in the classes. And there is one problem, which is it requires too many qubits. As you can see, so to represent a real number, we need R qubits. And if we substitute here, we need n more qubits. And it requires nr qubits, which is too much. And to solve this problem, we just simply split the matrix into 4 pieces, and which can reduce the number of qubits required. So by using such an iteration steps, and by dividing the matrices into 2, it can reduce the number of qubits required. So to compare it is on the table that original if we just use the nr qubits, original algorithm requires nr qubits, but if we use some kind of if we make an iterative algorithm that splits the matrix into 2, or D stands for the number of division of the matrix, and we can decrease the number of qubits required. And this is how the linear systems are solved in this paper. So we have to look at the results. So classical. So let me demonstrate the classical result, which is so to show the classical result. Wait, sorry. Oh, so let me demonstrate the classical result, which is seems actually made a MATLAB code that shows that solve the exact same equations, which is very easy. So yeah. So to show the initial condition, it just seems like this. So yeah, at the h are 0 and at the x equal L and y equal L, it is linearly increasing the temperature. And we have made the heat source distribution right randomly. So these are our heat source distribution, which is randomly distributed. Yeah, and it shows like this. Now I will run this code. And yeah, this is how it is becomes converging. Yeah, and this is convergent thing. Yeah, and yeah, this is the result, convergent result, and yeah, it seems like this. And to plot the error, it actually converges very fastly. So let's just seem like, so I made 1,000 iterations, but as you can see, yeah, even at the maybe 60 or 80 iterations, it converges very fastly. And yeah, we can see that we can check that it converges very well. So these are classical results, which is very easy to make. And but what we have to focus on is the error. So classical algorithms, the error really converges fastly and actually pretty works well. But if we look at the results that uses the qubits, it is kind of surprising that actually classical method actually converges much more faster, and it seems much more better. And I will tell the reason later. So these are one of the results that surprised me, which seems like a classical thing works much better. And another thing that this paper tried is that this paper reduced the range of the real number that is able to represent it, which is 2CI. And by reducing the range by 20%, it actually converges, it shows actually much better performance, which converges literally similarly like classical models. So by looking at these results, we can actually conclude that increase of a qubit doesn't ensure the smaller errors, and actually more noise if more qubits are involved in the numerical representation of such a real number. So yeah, and so this was the result of this paper. And my thought about the result is that, in my opinion, that I think the comparing the iteration step was too small, I think, because this is the exact result that I took it from the paper, that it only iterates only for 10 times, which is, in my opinion, this is too less iteration steps. And another thing I want to point out is that the scale of the experiment was too small to conclude any result. Like, so this experiment uses some kind of grid that was 11 by 11, which was 221 grids, and it is too small. The grid size is too, like, the scale of this experiment is too small to like conclude the general statement about any opinion, I think. So this is the last page was just my thought about this paper. Yeah. Thank you for listening. Any discussions or questions? Please?
I have one question.
Yeah.
About the plot that you showed.
Oh,
So in the plot, it says there are like 2,003 qubits. Well, I meant
Oh, sorry.
Yeah.
Yeah.
It says like 3 qubits, 5 qubits, and 7 qubits. So what are those numbers represent in this plot?
That stands for the yeah, I told you that to represent a real number, it takes a qubits to represent a real number. So that 3 and 5 and 7 is that number. How much qubits are used to represent the real number. Yeah.
I actually have two questions.
Yes.
The first one is, how do you calculate the error? Like, what are you comparing? What are the two things you're comparing to get the error?
Oh, how the error is defined. At the paper, it is defined as excuse me, yeah, here. As you can see, it's yeah, like like the yeah, Kate iteration steps and the real analytic solution and the difference between them.
Okay.
And
The second question is there some is there some reason that we need to use the quantum annealer for matrix inversion to solve linear systems of equations? Is there like a proven result that annealers are good for this?
that at the paper it states that I actually forgot the algorithm, but what is it? H start with the H that
Yeah, there's the HHL.
yeah. That that like it is a HH algorithm that actually involves them in matrices. But the problem was that this HH algorithm returns the quantum state, not a real number. So yeah, that was the problem that this people use the annealer, but I think it doesn't really work that much well.
Okay.
Just my.
I just wanted to know if there's a time complexity or some results that show that annealer is good for this. I mean, because if you use the same mapping, I think that you can still use the HHL algorithm for this case. Like when you change the continuous values and discretize them into like those types of conditions, I think you can actually use the HHL. But that's what I want to know why they use annealer.
Oh, I see. Yeah.
I have a question.
Yes.
Actually, I'm new to the quantum. I don't really know about this. So, can you explain why the equation 5 can approximate its components of the vector x?
그러니까 그 이게 그러니까 한국말로 할까? 그러니까 어려가지고 이게 아이고 사실 저도 조식을 정말 정확하게 자세하게 이해 못했는데 근데 이게 저희가 이제 x라는 이제 n 디멘션 벡터가 있으면 이제 그 각각의 컴포넌트가 이렇게 되는 거거든요. 근데 아마 제 생각에는 이게 2의 마이너스 r승도 있고 이러다 보니까 아마 뭐냐 r 디지트 이진수를 저렇게 그러니까 큐비트를 써가지고 저렇게 표현한 다음에 그다음에 맨 앞에 상수를 곱하고 그다음에 다시 보정해주는 상수를 빼주면은 리얼 넘버가 된다라고 저는 이해를 했습니다.
그럼 그걸 리얼 넘버로 나타내기 위한 툴이라고.
네네네, 이거는 그냥 그쵸. 라고 저는 이해를 했는데 사실 이게 정확한지도 잘 모르겠습니다. 이 부분은 저도 잘 받아들였는데 네. 혹시 yeah.
And usually
사실 저도 그거를 사실 그러니까 저도 왜 그냥 정말 저도 사실 그냥 리니어 시스템 푸는 게 더 쉽다고 생각하는데 네. 저도 사실 그 부분은 잘 모르겠습니다. 죄송합니다. 네. I actually have a yeah, I don't know. Sorry. I'm sorry. Yeah.